In this video, I want to talk a couple of things that I didn't cover in the last video. The first one is the direction of the velocity is always tangent to the path of the motion. Just imagine that the object is kind of moving. Let's say it's kind of following this kind of curved path like that. Then if we say this is our reference point, then you can make like a position vector like that. Over the course of time, the object will change its position. The next time the object just moved that point, then your position vector change. So let's say this is r prime. Then if you want to get the velocity is just derivative of your position vector like that. So in definitions, that is delta time goes to 0, then this is delta r. So delta r is the change in the position vector, position r, and let's say this is my another position r. Then the change in position, okay, then the change in position is this one. This is position change in position delta r. But if the delta t is very small, then this is delta r. If delta r is getting smaller and smaller, the direction of the r must be tangent to the path of the motion, right? So that's the direction of your delta r. So that's why the direction of your velocity is the same as direction of delta r. As it moves through any curved path is always tangent to the path of the motion. In here, let's say your object move this kind of curved path, okay? Then in order to analyze this curvilinear motion using polar coordinate system, you have to make this kind of r vector, okay? So this is r, and this is a unit vector of radial direction, and then the perpendicular direction is transverse direction, and this is your theta. Then you know that the velocity of the object is always tangent to the path, so the physical actual velocity is like that. Then as long as you describe the motion using polar coordinate system, your velocity, radial component, and r vector, and then transverse component and u theta vector, which means you have to break down your vector v along the radial direction and transverse direction. So if I break down along the radial direction, so it's like that. So this one this should be the radial direction component of your velocity, and then if I just break down here, so this one should be transverse component of your velocity, right? So this one is the VR and the v theta, the component, each component along each unit vector. Then just imagine that identical motion. So on left side, I just want to copy identical motion. So this one is just, in general, if you want to use just Cartesian coordinate system, we describe everything using x and y, right? So that means this is my x. So let's say if this is your r vector, then this is my x and this is my y, right? And then the velocity is still the same as like that. The velocity is this one. Then if you just use the Cartesian coordinate system, then that means I want to break down my velocity along the x component of I and y component of j, like that. So what is x component? Because I have to break down my velocity along the x, so which means this is my x component and this is my y component. This x component, y component is here and here, so this is my unit vector I and this is my unit vector j. Please note that these are two motions are identical, and the velocity, physical velocity, is in this direction. But depending on what coordinate system you use, either Cartesian coordinate system or polar coordinate system, the way you resolve your vector into which directions can be different. But physical quantity is still same. But depending on whether you use different coordinate system, maybe the analysis of vector will differ. Then let's look at the circular motion. Circular motion is one of curvilinear motion. So that means the object just moved along this circle path. Then this is your kind of velocity, okay? This is your r and this is theta. Then in the previous video, we know that the velocity is r dot ur and then r theta dot u theta. If we know time rate of change of r, time rate of change of theta, then we can get velocity and acceleration. A circular motion, because r is always fixed, that's why the r dot and r2 dot is all 0. Okay, so that's why the v square is equal to r theta dot u theta. Okay, and then we know that, and then a acceleration is minus r theta 2 and then r theta 2 dot. Okay, what is r theta 2 dot? That is angular acceleration. Angular velocity, okay, angular velocity is just r theta dot, because this is time rate change of your theta. That's the velocity. Then if you take one more derivatives, that becomes acceleration. That's why this one is angular acceleration, revolving around the center with a constant angular velocity. Then this angular acceleration will also goes to 0. Then this equation becomes like the v is just r theta dot u theta, and a velocity is negative r theta square ur. That's it. Then if we manipulate it, because we know that r theta dot is v, so this one can be written like the v square over r ur. Then why we have a negative here? Radial direction is out like that. This is ur. Negative means your acceleration is actually going directing toward the center. That's your acceleration. Why the acceleration is directing to the center? Because whenever this kind of object move, the velocity is here. That's your velocity. But the next time when the object move a little bit, the velocity is changing the direction. Okay, like that. So let's say this is a v velocity prime, and this is original velocity v, and then this is v velocity prime. Then the change of the velocity, the change in velocity is this going down this direction, delta v, right? So delta v over delta t is acceleration. That's why this directional delta v is the same as direction of the acceleration that goes to the center position. Okay. Until now, I showed you how we utilize the polar coordinate system to analyze the circular motion. But when it comes to curvilinear motion in general, it's not like a circular motion. The curved path could be any random path, like shown in this slide. So it is sometimes convenient to resolve the acceleration into component directed respectively along the tangents and the normal to the path of the particle. So right now in here, the object move along this kind of curved, general curved path. Then I told you that the velocity is always tangent, okay? And then the normal component is perpendicular to the tangent line. So the normal should be in this direction. So this is normal. And in here, this should be normal like that. So sometimes it's better to analyze everything along this tangent and normal, because we already know the velocity, and the velocity is tangent to the path. So we just resolved the accelerations, for example, into the velocity direction and its normal direction, and so on. So in here, this is our accelerations at a given time, for example. Then the velocity direction is always tangent. That's why when we use normal and tangent components, then there's no any velocity along the tangent, along the normal direction, because velocity is always tangent to the path like that. But acceleration could be anywhere. So that's why if you want to break the acceleration into the tangent to the normal, then you can have tangential component of acceleration and normal component of acceleration. Okay. So acceleration itself can be broken into the tangential. Okay. So this is tangential component, and this is a normal component. Then this tangential component of acceleration is the time rate change of your velocity, because your velocity is always tangent. Okay, the velocity only exists along the tangential direction. That's why the tangential component, we know that there should be time derivative of your velocity, the instantaneous velocity, right? But how about the normal directional acceleration? How we determine the normal directional acceleration on in this case? Just imagine that your object just move along this general path. Okay, right now this is not circle, this is just general path. But if you look at its very small segments that comprise all those kind of paths, so each segment ds is formed from the arc of associated circle having a radius of curvature rho. Okay, so like shown here, at this small ds is a part of this circle, right? If you think about ds is very small. And then in here we have the curvature is a little bit different. This is more slowly changed. So this ds as well is part of the radius of part of the another circle that has different rho. Okay. So we just imagine that as the object move, those kind of rho, radius of curvature, is keep changing. But we can just imagine that any ds, any given ds, can be part of this kind of virtual circle. Then if we can determine the rho, we can determine the normal component of acceleration. When we talk about the polar coordinate system, your acceleration is negative square v squared over r ur, right? So this is always directed to the center, which is normal directional kind of component of accelerations. So likewise, this is your tangential component of accelerations, and this is tangential component of accelerations. But at least the normal components is determined by v squared over rho. This rho is just radius. This rho is the radius curvature at this time. And at this time, because the radius curvature is different, that's why normal component of acceleration an is determined by another rho, and also the velocity might be different from here to here. So in this one, at any given time, we can compute the normal component of acceleration. Then the problem is how we can get those kind of rho. Let's say this is kind of curved path, okay, and then this curved path has a function of y, okay. For example, the curved path can be expressed as y is equal to fx. So that means as x change, your y value change. So if we can define any curved path in this form, then the radius of curvature rho at any point on the path can be calculated from this equation. Okay, so this is derivative of y with respect to x, and this is second derivatives. As long as you know the result of derivatives, then you can get the rho mathematically. In this example, a roller coaster travels along the vertical parabolic path defined by the equation. At point B, it has speed of 25 meters per second. So right now we know that this tangential speed, this is 25 meters per second, which is increasing at the rate of 3 meters per second. That means we know that tangential components AT, okay? So AT is 3 meters per second square. Okay, then what is the magnitude of the roller coaster acceleration when it is at point B? So point B is x is 30. So in this case, we can use Cartesian or polar, but right now, since the tangential component velocity is known, and the tangential component of acceleration is given as well, then when you just determine the magnitude of acceleration, it's convenient to use normal tangential components. Then right now we have to use that. So in a case, your acceleration is tangential component ut is tangential component unit vector, and then normal component acceleration and un, like that. So in here, this one should be ut, and this part is un, okay, unit vector like that. And then we already know that tangential component is 3 meters per second square, and then normal component is v squared over rho un, okay. Then we already know the velocity and what is the rho. So I show you in the previous slide that this one can be found by this equation. This is power and y second square magnitude. Then we know the y function here. So y dot is 0.02x, y second dot is 0.02, right? So if you just plug that 0.02, x is here, and then this is square, and then to the power of 3 over 2, and 0.02 magnitude, okay? So if you plug 30 into this x, then this is 79.3 meter. So that means at this point, this curvature has the radius of curvature, which is 79.3. So that's why your normal component acceleration is 25 square and then 79.3. That's it. That's normal components. So this one asks you the magnitude. That's why you have to look at the magnitude of A. So that is 3 square and 25 square and 79.3 and square. This is tangential component, normal component, and then this is meter per second square.